These are the worlds, in our own solar system and beyond it, that came close enough to growing life that scientists are still arguing about what actually happened on them. Mars once held an ocean bigger than the Arctic, and it's still leaking an unexplained gas into its atmosphere today. Venus may have stayed livable for 3 billion years before it cooked itself alive, and its clouds are still at the center of a live scientific fight. 2 icy moons of Jupiter and Saturn are hiding oceans right now, under miles of ice, in total darkness. A 4-billion-year-old rock, blasted off the surface of Mars, once convinced a room full of NASA scientists that they were looking at fossils from another planet. And 41 light-years away, 2 separate exoplanets are generating that exact same argument all over again, right now, in real time. None of it has ended up with anything scientists can point to and confidently call life. But every one of these worlds got close enough that the question still isn't settled, and by the end of this video, you'll understand exactly why. If any of this grabs you, go ahead and hit subscribe, because we cover stories like this one every week. Every world in this video sits somewhere on the same basic spectrum, between the 2 most extreme outcomes a planet or moon can have, and by the time this video ends, you'll have a working sense of exactly where each one currently sits on that spectrum, and why the scientists studying them still can't say for certain. On one end, a world stays sterile forever, never accumulating the ingredients or the conditions life needs, the way most objects in the solar system, most asteroids, most airless moons, almost certainly have. On the other end, a world crosses the line completely and actually produces something alive, the way Earth did at least once, roughly 3.5 to 4 billion years ago. Everything in between those 2 outcomes, a planet that had the ingredients but never quite crossed the line, or a planet that might have crossed it and then erased almost all the evidence, is where this video lives. And it turns out that middle ground is far more crowded and far better documented by actual spacecraft data than most people realize. Let's start with the planet everyone already has an opinion about, and the one that turns out to be even wetter than most people realize. For most of the last century, Mars was treated as the disappointment of the solar system, a cold red desert that never had much going for it. That reputation has been quietly falling apart for the last 20 years, and it kept falling apart right through 2025 and into 2026. The picture that's replaced it is a planet that once looked shockingly like Earth, with rivers, deltas, and by some estimates, an ocean covering nearly half its surface. The case for that ocean rests on 2 separate kinds of evidence, and they've been building on top of each other for decades. The first kind is mineralogical. Certain minerals only form in the presence of liquid water, and orbiters and rovers have found them scattered across the Martian surface in quantities that are hard to explain any other way. The second kind is physical. River cars carve particular shapes into the ground, deltas fan out in particular patterns where moving water meets a standing body, and shorelines leave behind particular kinds of terraced, layered deposits. Mars has all 3. In a study published in the journal NPJ Space Exploration, a research team led by Ignatius Argadestia, a PhD student at the University of Bern's Institute of Geological Sciences, identified what they called scarp-fronted deposits inside Valles Marineris, the vast canyon system that cuts across the Martian equator. These deposits look almost exactly like river deltas here on Earth, the fan-shaped buildup of sediment that happens where a river slows down and empties into a lake or a sea. Argadestia put it plainly, the structures his team found are clearly the mouth of a river into an ocean. What makes this particular study convincing to a lot of skeptics is the elevation data. Every one of these scarp-fronted deposits sits at roughly the same height, whether you find it deep inside Valles Marineris or out in the northern lowlands hundreds of kilometers away. That kind of consistency is exactly what you'd expect if they were all once shorelines of the same standing body of water, because water finds its own level no matter where you measure it. Fritz Schlunegger, one of the researchers on the project, was careful to note that this isn't the first time someone has proposed a Martian ocean. What's changed is the precision of the data. As he put it, earlier claims were based on less precise data and partly on indirect arguments. This time, the argument is built on some of the sharpest orbital imagery ever captured of the planet, pulled from 3 different spacecraft. the European Space Agency's ExoMars Trace Gas Orbiter, its Mars Express probe, and NASA's Mars Reconnaissance Orbiter. The dating on all of this points to a specific and surprisingly narrow window of Martian history. The deposits formed during the transition between the late Hesperian period, which ran from about 3.7 billion years ago, and the early Amazonian period, which started around 3 billion years ago and technically continues into the present. Within that window, researchers pinned the shoreline formations to roughly 3.37 billion years ago, which the study's authors describe as the moment when Mars had the largest amount of surface water it would ever have again. Based on the elevation of these deposits, the ocean they were tracing would have covered Mars's northern hemisphere to a depth ranging from about 3,650 to 3,750 meters below the surrounding terrain, and by the researchers' own estimate, the resulting body of water rivaled the Arctic Ocean here on Earth in total size. This isn't an isolated finding sitting alone in the literature. A team at the University of Arkansas, led by Geosciences PhD student Corey Hughes, approached the same question from a completely different angle in 2025 and landed on a similar answer. Hughes and his colleagues compared the physical structure of Martian river rocks to sandstone left behind by a river that flowed across northwest Arkansas roughly 300 million years ago. The comparison let them study how backwater zones, the slow-moving stretches near a river's mouth, behave in real geological formations, and then check whether Mars showed the same signatures. It did. Hughes summed up why any of this matters in a single sentence that's about as close as planetary science gets to plain talk. We don't know of any life forms on Earth, or anywhere in the universe, that don't require liquid water. So the more liquid water we have on Mars, a simple argument could be made that you have a higher chance of life. Then, in February of 2025, the evidence stopped being purely a matter of orbital photography and became something closer to fieldwork. China's Zhurong rover, using ground-penetrating radar, traveled about 1.9 kilometers, a little over a mile, roughly perpendicular to a set of escarpments long suspected to be an ancient shoreline. What the radar found underground were thick, sloping layers that matched the structure of beach deposits on Earth, almost line for line. Michael Manga, one of the scientists involved in interpreting the data, explained the physical process behind what Zhurong detected. The sand that's on those beaches is coming in from the rivers, and then it's being transported by currents in the ocean, and continually being transported up and down the beaches by the waves coming and going up and down the beach. That's not a description of a dry, dead world. That's a description of an active coastline with tides, currents, and wind-driven waves on a planet where none of that exists today. Hai Liu, a professor at Guangzhou University who worked on the same findings, drew the connection to Earth's own biological history directly, noting that scientists believe life first emerged in exactly this kind of setting, at the boundary between air and shallow water, and that the Zhurong data strengthens the case for past habitability in this region on Mars. None of this is only about the surface. Well before any of these 2025 and 2026 findings, NASA's Curiosity rover had already been sampling the floor of Gale Crater, an impact basin that, sometime between 3.5 and 3.8 billion years ago, held a standing lake fed by rivers flowing in from the surrounding highlands. It's worth remembering just how long Curiosity has now been parked inside that single crater, patiently drilling and analyzing one rock at a time since landing there in August of 2012, which means the picture of Gale Crater's ancient lake described in this video isn't the result of one quick flyby or one dramatic announcement. It's the accumulated product of well over a decade of slow, methodical, rover-scale fieldwork on the surface of another planet, the kind of patient data collection that rarely makes headlines on its own, but that every single one of the bigger, more dramatic Mars discoveries in this video ultimately rests on. Curiosity's instruments were able to pin down the actual chemistry of that ancient lake water: sodium, potassium, magnesium, and calcium ions, along with chloride, sulfate, and bicarbonate, plus trace amounts of zinc, manganese, copper, and iron. That's not just confirmation that water was there. It's a detailed enough chemical fingerprint that researchers have been able to build models testing whether specific kinds of microbes, ones that survive by cycling iron between different oxidation states, could theoretically have made a living in that exact lake. That Gale crater chemistry has already been put to direct scientific use, not just catalogued. Researchers have taken two specific, well-studied Earth microbes, one called Geobacter sulfur-reducens and another called Rhodopseudomonas palustris, both organisms capable of surviving by cycling iron between different chemical states rather than relying on sunlight, and built detailed computer models of their metabolism using the actual water chemistry Curiosity measured inside Gale crater. The point of that modeling work wasn't to claim these exact organisms ever existed on Mars. It was to test something more specific and more useful. Whether the ancient lake water inside Gale crater, as far as its chemistry alone is concerned, could have supported this general style of iron cycling metabolism at all. The modeling suggested it plausibly could have. That's a meaningfully different and more rigorous kind of claim than simply saying water once existed there, because it ties Mars's ancient chemistry directly to a specific, testable biological process, rather than leaving habitability as a vague, generic label. So where does that leave the ocean question? It leaves it strong, but not settled, and it's worth being honest about that, rather than pretending the debate is over. Researchers have been arguing about the existence of Martian shorelines since the Viking orbiters first returned high-resolution images decades ago, and one persistent problem for the ocean hypothesis has always been elevation. Some of the proposed ancient shorelines, when you map them out across the planet, show large and inconsistent variations in height over relatively short distances, which is the opposite of what you'd expect from a genuine sea level line. That inconsistency is exactly what makes the new scarp-fronted deposit data, with its unusually tight elevation matching, so significant to researchers on the ocean side of the argument. But it hasn't ended the conversation, and it probably won't until a mission physically drills into one of these formations and settles the mineralogy on the ground. What we're left with, as of the most current research, is a planet that most likely had a genuine ocean, warm enough and long-lived enough to matter, somewhere between 3 and 4 billion years ago. Whether anything ever lived in it is still an entirely open question, and it's one we're going to come back to later in this video, because a single meteorite blasted off this exact planet 16 million years ago once convinced some of NASA's own scientists that the answer might be yes. All of this ocean evidence matters, for reasons that go beyond settling an old scientific argument, too. Every new confirmation of where Mars once held standing water helps mission planners narrow down exactly where to look for the strongest possible evidence of ancient life, and exactly which rock samples are worth the enormous cost and difficulty of eventually hauling back to Earth. A shoreline dated to 3.37 billion years ago, or a beach deposit found by ground-penetrating radar, isn't just a historical curiosity, it's a map, effectively pointing future rovers and future sample return missions toward the specific handful of locations on an entire planet where billions of years ago, conditions were actually good enough that something might have lived there. That's exactly the logic that sent NASA's Perseverance rover to Jezero crater in the first place, a location chosen specifically because orbital data showed clear evidence of an ancient lake and river delta, the same category of evidence this entire section has been walking through. We'll come back to what Perseverance found there later in this video, because it turned into one of the most talked about Mars discoveries of the last several years. For now, we're leaving the red planet behind and heading somewhere far stranger, a world that might have spent 3 billion years as comfortable as Earth before turning into the most hostile place in the solar system. Venus sits right next door to Earth, almost exactly the same size, almost exactly the same mass, built out of almost exactly the same raw material when the solar system was forming. For a long time, that similarity was treated as a coincidence, with no real consequences, because the Venus we can actually observe today is about as far from Earth as a planet can get. The surface temperature averages 462 degrees Celsius, which is 864 degrees Fahrenheit, hot enough to melt lead. The atmospheric pressure at the surface is 93 times what you feel standing at sea level on Earth, roughly the same crushing force you'd experience nearly a kilometer underwater. And the whole planet is wrapped in thick clouds of sulfuric acid. None of that sounds like a place that was ever hospitable to anything. But the deeper scientists have dug into Venus's early history, the more that first impression has started to look misleading. The first hint that Venus wasn't always like this came out of NASA's Pioneer Venus mission, which began in 1978. Measurements taken during that mission, later analyzed through the 1980s, showed an unusual ratio of deuterium to ordinary hydrogen in the Venusian atmosphere. Deuterium is a heavier form of hydrogen, and it doesn't escape a planet's gravity as easily as the lighter, more common version does. When you find an atmosphere that's unusually enriched in deuterium, it's often a sign that a huge amount of ordinary hydrogen has been lost to space over time, hydrogen that most likely came from water. The implication was straightforward, even if it took decades to build a full case around it. Venus once had an ocean, and that ocean is gone now because the water that made it up was slowly torn apart and vented into space. That single data point sat mostly on its own for years, until climate modeling caught up to it. Michael Way and Anthony Del Genio, both at NASA's Goddard Institute for Space Studies, built a series of climate simulations that tried to reconstruct what early Venus might actually have looked like, first presenting results in 2016, and then expanding the work substantially by 2019. They ran 5 separate scenarios, each with a different amount of surface water, ranging from a deep ocean averaging just over 1,000 feet in depth, down to nothing more than a shallow layer locked into the soil. Every single one of the 5 scenarios produced the same basic result. Given the topography Venus has today, and accounting for how much sunlight the planet receives at its distance from the Sun, the climate model showed Venus could have sustained a temperature range of roughly 20 to 50 degrees Celsius, a genuinely temperate, livable range, for as long as 3 billion years. Under this model, Venus may have remained comfortable enough for liquid water on its surface until somewhere around 700 million years ago, which in the timeline of our solar system is remarkably recent. If that's accurate, Venus wasn't a marginal, borderline case for habitability. It may have spent most of its history as one of the most stable, long-lived habitable environments this solar system has ever produced, arguably more stable than early Earth, which was busy getting hit by asteroids and reorganizing its own crust during a lot of that same stretch of time. So what actually killed it? The mechanism researchers point to is what's called a runaway greenhouse effect, and it's worth walking through because it's one of the clearest cautionary examples of planetary climate collapse we have. As the young sun gradually brightened over billions of years, the extra heat it delivered to Venus, sitting closer to the Sun than Earth, eventually pushed surface temperatures high enough that ocean water began evaporating faster than it could be replaced through rainfall. Once enough water vapor built up in the atmosphere, it trapped even more heat, which evaporated even more water, in a feedback loop that had no natural break. As that water vapor rose into the upper atmosphere, ultraviolet radiation from the Sun broke the individual water molecules apart into hydrogen and oxygen. The hydrogen, being extremely light, escaped the planet's gravity and drifted off into space permanently. With the water gone and the hydrogen gone with it, there was nothing left to pull carbon dioxide out of the atmosphere and lock it into rock the way it does on Earth through the ordinary carbon cycle. So the carbon dioxide just kept accumulating year after year, millennium after millennium, until it built the crushing, superheated atmosphere Venus wears today. There's a newer wrinkle to this story that only surfaced in mid-2025, and it flips part of the usual narrative around. A NASA-supported international research team proposed that Venus's ancient ocean may not have simply been a victim of the runaway greenhouse. It may have helped cause it. Venus today rotates once every 243 Earth days, which is longer than its own year, and makes it the slowest rotating planet in the solar system. According to this new theory, the sheer mass and tidal drag of an ancient ocean could have been the thing that slowed Venus's rotation down that dramatically in the first place. And a slow rotation changes cloud behavior in a way that matters enormously for climate. Slow spinning planets tend to build thick, highly reflective daytime cloud cover, which under the right conditions can actually help keep a planet cool and stable. But push that same slow rotation slightly further, change the cloud feedback just enough, and instead of protecting the planet, it can tip the balance the other way and accelerate a runaway greenhouse collapse. In other words, the very ocean that might have made Venus habitable for 3 billion years may have also been quietly loading the gun that eventually ended it. Some of the underlying physics behind these models goes back further than the 2016 and 2019 studies, and it's worth understanding where the numbers originally came from. Back in 1988, researcher James Casting ran an early radiative convective climate model and found that early Venus, receiving roughly 1.45 times the solar energy Earth receives today, a level Venus would have experienced around 3.8 billion years ago, would have settled into surface temperatures around 100 degrees Celsius under a modest 2-bar atmosphere of nitrogen and water vapor. That's hot by Earth standards, but still well short of an outright runaway greenhouse. Casting's own follow-up work suggested that cloud cover could have kept that scenario stable in what's called a moist greenhouse state, rather than tipping all the way into full runaway conditions. And it's that same cloud feedback mechanism, refined by decades of more sophisticated three-dimensional climate modeling since, that eventually became the basis for Way and Del Genio's more optimistic 3 billion-year habitability window. It's worth being upfront that this entire picture is genuinely contested within planetary science, not just a settled story that everyone accepts. Some purely one-dimensional, cloud-free climate models, run without accounting for cloud feedback effects at all, predict that Venus has essentially always sat inside a runaway greenhouse threshold, meaning it may never have had a stable ocean to begin with. Other researchers argue Venus went through a long-lived 100-million-year magma ocean phase early on, with a thick steam and carbon dioxide atmosphere, and that its water was dissociated and lost to space before a genuine liquid ocean could ever fully form and settle. A 2023 paper published in the Proceedings of the National Academy of Sciences described the underlying question in blunt terms, calling it a key uncertainty driving the design of upcoming missions to the planet. Multiple space agencies have missions in development specifically to try to resolve this, because right now, without a lander or an orbiter built to look for the right chemical signatures, the honest answer is that nobody fully knows which version of Venus's history actually happened. What almost everyone agrees on, whichever model they favor, is the ending. Whatever window of habitability Venus may have had, it's closed now, and it closed so thoroughly that the surface is arguably the single most hostile environment of any solid body in the solar system, worse in some respects than the vacuum of space itself. That makes Venus a genuinely strange case among the worlds in this list. It isn't a place where the question is whether conditions were ever good enough for life to get started. Increasingly, the science suggests conditions may have been good enough for an extraordinarily long time. The tragedy of Venus, if you want to call it that, isn't a world that never had a chance. It's a world that may have had 3 billion years of exactly the kind of chance Earth got, and lost it anyway. And Venus's story doesn't end with its ancient vanished ocean, because in 2020, something happened in Venus's clouds today, in the present tense, that briefly made this the most talked about planet in the solar system, and set off one of the messiest, most public disputes in recent astronomical history. In September of 2020, an international team of astronomers, led by Jane Greaves, an astronomer at Cardiff University, announced they had detected phosphine gas in the clouds of Venus. It's worth pausing on just how unlikely that announcement was to begin with, because Venus's clouds sit in one of the only genuinely temperate zones anywhere on the planet, roughly 50 kilometers up, where pressure and temperature both happen to land in a range not too different from parts of Earth's own lower atmosphere, even though the surface directly below is hot enough to melt lead. That narrow, cloud layer habitable band has been floated as a theoretical refuge for airborne microbial life for decades, long before anyone had the instruments capable of actually testing the idea, which is part of why Greaves's announcement landed with the force that it did. The detection came from two separate, independent telescopes, the Atacama Large Millimeter Array in Chile, known as ALMA, and the James Clerk Maxwell Telescope in Hawaii, and the signal showed up with a confidence level of 5 sigma from one instrument and 7 sigma from the other, statistical thresholds that scientists generally treat as strong evidence rather than noise. What made the announcement explode across news outlets worldwide wasn't the chemistry itself, it was what that chemistry implied. On Earth, phosphine is produced almost exclusively by anaerobic microbial life, or by industrial human processes. Finding it in the atmosphere of another planet, in meaningful quantities, is considered one of the most promising kinds of biosignature scientists know how to look for. For a few days in September of 2020, a real, peer-reviewed, published scientific paper was suggesting that the clouds of Venus might contain something alive. The backlash started almost immediately, and it came from serious scientists working in good faith, not internet skeptics. Within weeks, a team led by Geronimo Villanueva at NASA's Goddard Space Flight Center published a competing analysis arguing that Greaves's team had misread the data entirely and that the specific absorption line they'd identified as phosphine was actually sulfur dioxide, a completely mundane, non-biological gas that's extremely common in Venus's atmosphere. Villanueva's team went further than a typical scientific rebuttal and explicitly suggested, in their paper's own abstract, that Greaves's team should retract their original publication. That's an unusually aggressive move in a field where researchers normally let peer review and follow-up studies settle disagreements over time, and it was received that way by much of the astronomical community. The fallout got messy fast. The International Astronomical Union's own Commission F3 Organizing Committee released a public statement, and that statement itself proved so controversial among the Commission's own members that the IAU executive stepped in and had it retracted. Villanueva's team, for their part, later issued a formal apology, stating plainly, "We agree that the sentence calling for retraction was inappropriate, and we apologize for harm caused to the Greaves et al. Team," and explaining that the language had come from a misreading of a Nature Astronomy editorial guideline that had actually just encouraged them to post their critique publicly for open discussion. While that public dispute was still unfolding, Greaves and her colleagues went back into the original ALMA data and discovered it contained what they called a spurious signal, an artifact that could have thrown off their initial analysis. On November 16th of 2020, once a corrected version of that ALMA data was released, Greaves's team ran a fresh analysis and posted it publicly ahead of formal peer review. Their conclusion held up in its basic shape, but shrank in its confidence. They still found phosphine in Venus's clouds, just in a smaller quantity than they'd first reported. On almost the exact same day, a separate study out of Leiden University, published in the journal Astronomy and Astrophysics on November 17th of 2020, ran its own independent analysis of the same underlying spectral data and reached the opposite conclusion entirely, reporting no statistically significant detection of phosphine at all, and describing the original claimed signal as spurious. That left the scientific community stuck in an unresolved standoff for the next 2 years, with dueling analyses of the same handful of observations and no clean way to settle who was right. NASA's Stratospheric Observatory for Infrared Astronomy, known as SOFIA, a modified Boeing 747 that carries a telescope to the edge of the atmosphere for observations, was deployed specifically to try to break the tie. In November of 2022, SOFIA's results came back, and they didn't find phosphine either, adding more weight to the skeptical side of the debate without fully closing the case. Then, in August of 2024, the story took another turn. A team led by Dave Clements, an astrophysics reader at Imperial College London, presented new, not yet peer-reviewed findings at the UK's National Astronomy Meeting, built on a much larger set of observations gathered since the original 2020 discovery. Not only did Clements's team detect phosphine again, they also identified ammonia in Venus's clouds, at parts per billion concentrations deeper in the cloud layers than phosphine had ever been found. Ammonia matters here because, like phosphine, it's a molecule that shouldn't easily exist in Venus's harshly acidic, oxidizing atmosphere without something actively producing it. Clements summarized the puzzle honestly, rather than making a grander claim than the data supported. It means that there is some way in which hydrogen compounds are being produced in the atmosphere of Venus where they shouldn't be expected. When directly asked whether this pointed toward life, his answer was refreshingly candid for a field that sometimes gets ahead of its own evidence. "We can't say at this point whether it means life or not," he said, before putting rough numbers on his own uncertainty. In his estimation, roughly a 10 to 20% chance the signal traces back to biology, and an 80 to 90% chance it's some form of chemistry scientists simply don't understand yet. As of the most recent research available, that's still exactly where the phosphine question sits. Not confirmed, not disproven, revisited and re-argued by different teams using different instruments roughly every couple of years since 2020, with each new study shifting the odds slightly without ever delivering a knockout result in either direction. It's a rare case in modern astronomy where the uncertainty itself has become part of the story, a genuinely open scientific argument playing out in public, in real time, about whether the clouds of the hottest planet in the solar system might be hiding the one thing everyone's looking for. From a planet that might still be hiding something in its clouds today, we're now heading somewhere with a very different kind of evidence problem. A moon, where scientists aren't debating whether the ocean is there. They already know it is. What they don't know is what's swimming in it, if anything at all. Almost everywhere researchers find liquid water on Earth, they find life alongside it, which is exactly why the discovery that several moons in the outer solar system are quietly hiding oceans of their own reshaped the entire search over the past 3 decades. Planetary scientists now use a specific term for this category of world: ocean worlds, moons, and dwarf planets that hold genuine liquid water, not on their surface, but sealed away in their interior beneath a shell of ice. Jupiter's moon Ganymede and its moon Callisto both show indirect evidence of interior oceans of their own, based on how their magnetic fields behave, though with far less direct contact between that water and warm rock than scientists believe Europa has. Saturn contributes at least 2 known or suspected ocean worlds of its own: tiny Enceladus and giant Titan, both of which we're about to cover in detail. But of every single ocean world discovered so far, Europa is the one that first put this entire category on the map, and it remains the one scientists have built an entire flagship spacecraft specifically to study. Europa is the 4th largest of Jupiter's dozens of moons, roughly the size of Earth's own moon, and from a distance, it doesn't look like much, just a smooth, cracked, ice-covered ball streaked with reddish-brown lines. What's underneath that ice is the reason planetary scientists talk about Europa the way they talk about almost nowhere else in the solar system. Beneath a crust of water ice, several kilometers thick, sits a genuine global ocean of liquid salt water, and by current estimates, that ocean holds roughly twice as much water as every ocean on Earth combined. Europa is smaller than Earth, but because so little of its interior is rock and so much of it is water, it may actually contain more liquid water, in absolute terms, than our entire planet does. That ocean is also, in almost every sense that matters, completely alien from anything in Earth's oceans. It sits in total darkness, sealed off from sunlight by that thick ice shell above it, which means photosynthesis, the energy source that underpins almost the entire food chain here on Earth, simply isn't available to anything that might live there. Any potential Europan life would have to run on chemistry instead of sunlight. And there's a real reason to think the chemistry might actually be there to support it. Unlike some of the icy moons further out in the solar system, Europa's ocean is thought to sit in direct contact with warm rock at the seafloor, rather than being sealed off from the rocky interior by a separate layer of ice. That rock-to-water contact matters enormously, because it's exactly the kind of interaction that, on Earth, produces hydrogen and other chemical energy sources at deep-sea hydrothermal vents. The same vents that support entire ecosystems on our own ocean floor that have never seen a single photon of sunlight. The first hints that Europa's ocean might be more active than a sealed-off, static body of water came from NASA's Galileo spacecraft in the 1990s, which discovered jumbled, chaotic patches of terrain on Europa's icy surface, features that suggested the ice shell had been churned and disrupted from below relatively recently in geological terms. Then, in 2012, the Hubble Space Telescope captured what appeared to be plumes of water vapor erupting from Europa's surface, a tantalizing sign that material from that hidden ocean might occasionally be venting directly into space, the same way it does on Saturn's moon Enceladus. Scientists went back and reanalyzed older Galileo data from the 1990s in 2018, specifically to check for corroborating evidence of these plumes, adding more weight to the possibility without fully confirming it. NASA has now committed real hardware to answering these questions directly. The Europa Clipper mission, carrying 9 separate science instruments, is designed to conduct a long series of close flybys, roughly 50 of them by mission's end, skimming past Europa's icy surface to study its composition, its structure, and its habitability without ever actually landing. If any of those hoped-for plumes are active, and Clipper happens to fly through one at the right moment, some of its instruments are sensitive enough that they could, in principle, detect microbes directly in the ejected material, although even scientists working on the mission are careful to describe that outcome as a long shot, rather than an expectation. The European Space Agency is running a parallel effort called JUICE, short for Jupiter Icy Moons Explorer, which will study Europa alongside two of Jupiter's other large moons, Ganymede and Callisto, both of which are also suspected to hide oceans of their own beneath their ice, though with less direct rock-to-water contact than Europa likely has. Even landing on the surface someday wouldn't be enough to fully answer the question, which is why NASA has a program called SESAME, the Scientific Exploration Subsurface Access Mechanism for Europa, working on early-stage concepts for what are sometimes called cryobots, robotic probes designed to melt or drill straight through kilometers of ice and physically reach the ocean underneath. That kind of mission is still years, probably decades, away from actually launching, but it represents the honest endpoint of this whole line of research. Orbiting flybys and surface landers can tell scientists a great deal about Europa's chemistry and geology. Only a probe that actually reaches the liquid water itself could ever conclusively answer whether anything lives in it. There's also a strange, almost backwards silver lining buried in Europa's harsh radiation environment. Europa sits deep inside Jupiter's powerful magnetic field, and its thin, wispy atmosphere is under constant bombardment from that radiation. Ordinarily, radiation is treated purely as a threat to any potential biology, something that damages cells and breaks apart organic molecules. But at Europa, that same radiation continuously splits apart water molecules in the Moon's tenuous atmosphere, breaking H2O down into hydrogen and oxygen, and some researchers argue that process could actually help deliver a usable chemical fuel source down into the ocean below, not unlike the hydrogen that turned out to matter so much at Enceladus. Investigators studying Europa's ocean chemistry more broadly believe it's likely rich in dissolved ions, including magnesium, sodium, potassium, and chlorine, the same basic categories of dissolved salts that define ion-rich, salty environments where life thrives here on Earth. None of that confirms biology exists in Europa's ocean, but it means the ocean isn't just sitting there, dark and inert. It's chemically active, with energy and raw material potentially cycling into it from multiple directions at once. Even in just the last several months, new research has kept adding detail to the picture. A study published in January of 2026 proposed a previously unrecognized mechanism by which Europa's surface ice might slowly sink downward over time, carrying oxidants and other chemical ingredients from the surface into the ocean below, effectively feeding the deep ocean a steady trickle of the raw materials life would need. It's one more small piece of evidence suggesting that whatever's happening underneath Europa's ice isn't a sealed-off, chemically stagnant system, but something with an active exchange of material between the surface and the deep interior. Nobody has found life on Europa. Nobody has even conclusively confirmed the plumes are real and ongoing. But of every single body in our solar system, including Earth, Europa may hold more liquid water in contact with warm rock, shielded from sterilizing radiation and sitting there in the dark, than anywhere else we know of. That combination is exactly why NASA built and launched an entire billion-dollar spacecraft specifically to go stare at it, and exactly why, of all the ocean worlds in this video, Europa is the one most scientists would point to first if asked where they'd want humanity's first direct sample of an alien ocean to come from. If Europa represents a world where scientists are still waiting to confirm the basic ingredients are even present, our next stop is a much smaller moon where those ingredients have already been caught red-handed, spraying directly out into space, where spacecraft could fly straight through them and taste what's inside. If Europa is the ocean world that first proved this entire category existed, Enceladus is the one that turned the category from a theoretical inference into something a spacecraft could physically fly through and taste. Every conclusion scientists have drawn about Europa's ocean, its size, its salinity, its likely contact with warm rock, comes from indirect evidence. Gravity measurements, magnetic field readings, the way the moon's icy surface deforms under tidal stress. Nobody has ever directly sampled a single molecule from inside it. Enceladus is different, and it's different specifically because of its plumes, and that difference is what makes it, for now, the single best-studied ocean world in the entire solar system. Enceladus is tiny by the standards of this list, a moon of Saturn, only about 1/6 the size of Europa, small enough that nobody expected much from it when NASA's Cassini spacecraft arrived in orbit around Saturn in 2004. What Cassini found there turned into one of the most detailed, most patiently assembled scientific detective stories of the entire mission, built flyby by flyby over more than a decade. The first clue came in February of 2005, during Cassini's first close pass of Enceladus, when it flew within 725 miles, about 1,167 kilometers, of the tiny moon. The spacecraft's magnetometer picked up something odd, a localized bending in Saturn's magnetic field directly above Enceladus, the kind of distortion you'd expect to see near a comet with its own thin atmosphere, not near an inert ball of ice barely 300 miles across. Linda Spilker, one of Cassini's project scientists, later described that first reading in vivid terms. The magnetic field lines were standing off from Enceladus's surface, more like you'd see with a comet, but just at the South Pole. 1 month later, in March of 2005, Cassini flew past a second time, and the same magnetic distortion showed up again, this time alongside direct detections from the spacecraft's cosmic dust analyzer, which picked up thousands of tiny dust-sized particles in the space around the moon. Cassini's cameras, meanwhile, had spotted a set of long, linear fractures near Enceladus's south pole with a different color and texture than the rest of the moon's surface, features that looked geologically young rather than ancient and weathered. Piece by piece, across dozens of subsequent flybys, the picture assembled itself. Enceladus wasn't an inert snowball. It was actively venting material into space, through cracks near its south pole nicknamed tiger stripes, in the form of towering geyser-like plumes of water vapor and ice particles, plumes energetic enough that some of that ejected material continuously feeds one of Saturn's faint outer rings, called the E-ring. Cassini's composite infrared spectrometer measured the heat coming off the fractured south polar region directly, and found somewhere between 3 and 7 gigawatts of thermal energy radiating out of that relatively small area, confirming Enceladus has genuine internal heat, generated most likely by tidal flexing as Saturn's gravity squeezes and stretches the little moon on its orbit. That made Enceladus only the third solid body in the entire solar system, after Earth and Jupiter's volcanic moon Io, where internal heat has been detected directly from orbit. Cassini didn't just fly near the plumes. Mission planners deliberately adjusted its trajectory over the following years to fly directly through them, sampling the material with onboard instruments as it passed. What Cassini found inside those plumes reads almost like a checklist of ingredients an astrobiologist would ask for. Water, overwhelmingly, in the form of tiny ice grains, organic and nitrogen-bearing molecules, including acetylene, ammonia, methane, and carbon dioxide, and silica grains of a specific size and structure that, on Earth, typically only form through a particular kind of chemical reaction between hot rock and alkaline seawater, the same reaction that powers hydrothermal vent systems on our own ocean floor. That silica finding implied something important was still missing from the data, because that same hot rock and seawater reaction should also release hydrogen gas, and Cassini's instruments hadn't detected it, at least not under normal operating conditions. So on October 28th of 2015, during Cassini's final and deepest dive through the Enceladus plume before the mission's later years wound down, engineers switched the spacecraft's ion and neutral mass spectrometer into a special operating mode specifically to hunt for hydrogen. This time, they found it, and in substantial quantities, published in the journal Science in 2017 by lead author Hunter Waite. Hydrogen matters here because it's a usable chemical energy source, the kind certain microbes on Earth, called chemolithotrophs, can metabolize directly without any sunlight at all, the same class of organisms that thrive around Earth's own deep-sea hydrothermal vents. Waite, describing the discovery afterward, put it about as memorably as any planetary scientist has ever described a data point. Although we can't detect life, we've found that there's a food source there for it. It would be like a candy store for microbes. Thomas Zurbuchen, at the time an associate administrator overseeing NASA's Science Mission Directorate, called it, in a public statement, the closest we've come, so far, to identifying a place with some of the ingredients needed for a habitable environment. Even that turned out not to be the last chapter. Cassini's mission at Saturn ran from 2004 until 2017, and scientists have continued mining its recorded data long after the spacecraft itself was deliberately plunged into Saturn's atmosphere to avoid any risk of contaminating Enceladus with Earth microbes. In June of 2023, an international research team went back through measurements from Cassini's cosmic dust analyzer, focusing this time on ice grains sampled not from the plume directly, but from Saturn's broader E-ring, where a much larger volume of particles had accumulated over the years, giving researchers a bigger dataset to work with. Inside some of those grains, they found sodium phosphates, chemically bound molecules containing sodium, oxygen, hydrogen, and phosphorus. Phosphorus matters because it's one of the essential building blocks of life as we understand it, a core ingredient in DNA, RNA, and cell membranes, and until this discovery, it had never been detected in any ocean beyond Earth's own. Follow-up laboratory experiments, run by co-authors in Europe and Japan, went further and estimated that Enceladus's ocean likely holds phosphorus, dissolved in various phosphate forms, at concentrations at least 100 times higher than what's found in Earth's oceans. It's worth sitting with how strange the timeline of that particular discovery actually is. Cassini stopped collecting data at Enceladus years before that 2023 phosphorus paper was ever published, and the spacecraft itself had already been destroyed, deliberately, on purpose, back in 2017. Every bit of that phosphorus evidence came from a research team combing back through archived measurements the spacecraft had already sent home, years earlier, sitting in a dataset that nobody had fully mined for this specific chemical signature yet. That's not a rare occurrence in this field. It's close to the norm. A striking share of the discoveries covered in this entire video, the Enceladus hydrogen finding, the phosphorus finding, large parts of the Mars ocean case, even portions of the ALH 84001 reanalysis, came not from a brand new spacecraft arriving at a brand new destination, but from scientists returning to data that had already been collected, sometimes years or decades earlier, and asking it a more specific question than anyone had thought to ask the first time around. One of the earlier pieces of this puzzle, easy to overlook next to the more dramatic hydrogen and phosphorus findings, came from Cassini's ion and neutral mass spectrometer identifying ammonia inside the plume back in 2009. Ammonia might sound like a minor detail, but it plays a specific and important role here. It acts as a natural antifreeze, lowering the freezing point of water and helping explain how Enceladus can maintain liquid water at all, this far from the Sun, inside a moon that small. Cassini's infrared instruments measured temperatures exceeding 180 degrees Kelvin near the fractures where the plumes actually erupt, warm enough, especially with ammonia mixed in, to keep water in liquid form long enough to feed the geysers continuously, rather than just venting out as a one-time burst. Put together with the later hydrogen and phosphorus discoveries, the ammonia detection helped confirm this wasn't a fluke or a one-off event. It was consistent, ongoing evidence of a genuine liquid ocean, actively interacting with warm rock, sustained over the entire period Cassini was watching. Line them up together, and Enceladus has now delivered nearly every individual ingredient scientists look for when they assess whether an environment could support life: liquid water, organic and nitrogen-bearing molecules, a usable chemical energy source in the form of hydrogen, and now phosphorus, in genuinely striking abundance. What Enceladus has not delivered, and what no mission has yet been built specifically to look for, is any direct evidence of an actual organism. Spilker, reflecting on the whole arc of the discovery, called it a great detective story, adding that it took all of the instruments on Cassini to put together the puzzle and help us learn what we know about Enceladus today. It took the whole team working together. Right now, of every ocean world in this list, Enceladus has the single strongest chemical case for habitability that's ever been assembled. Nobody has confirmed anything is actually living in it, but for the first time, nobody can honestly say the ingredients aren't there. It's worth appreciating how strange it is that this level of direct evidence exists at all. Enceladus is a moon roughly 310 miles across, smaller than the state of Arizona, orbiting nearly 900 million miles from the Sun, and a spacecraft built and launched in the late 1990s managed to fly directly through material erupting from its interior ocean and identify individual dissolved compounds inside it, down to specific salts and organic molecules. That's not a measurement anyone on the original Cassini mission team expected to make when the spacecraft launched in 1997, years before the plumes had even been discovered. It's the kind of result that only came from decades of patient, incremental observation. One flyby revealing a magnetic anomaly, the next revealing dust particles, the next revealing organic chemistry, each new pass building directly on everything learned before it, until an entire ocean's chemical fingerprint had been assembled, one flyby at a time. Not every world on this list is built around liquid water at all, though. Our next stop trades water for something almost nobody expected to matter this much. A moon with rivers, lakes, and rain, just made out of chemicals that would instantly freeze solid on Earth, and a set of findings that took planetary scientists most of the last 2 decades to fully appreciate, ever since the first spacecraft finally managed to see past its haze. Titan is Saturn's largest moon, bigger than the planet Mercury, and it holds a distinction that belongs to nowhere else in the solar system besides Earth itself. It has a genuinely dense atmosphere, about 1.5 times the surface pressure of Earth's, and stable liquid on its surface, gathered into rivers, lakes, and seas. From orbit, with its hazy orange atmosphere and its networks of branching waterways, Titan can look almost startlingly Earth-like. Step onto the actual surface, and that resemblance falls apart immediately, because the surface temperature sits between 89 and 94 degrees Kelvin, somewhere around 183 to 179 degrees below 0 Celsius. And every one of those rivers, lakes, and seas is filled not with water, but with liquid methane and ethane. The atmosphere driving all of this is roughly 95 to 98% nitrogen, with methane making up another 2 to 5%. High above the surface, sunlight and energetic particles streaming in from Saturn's magnetic field tear those nitrogen and methane molecules apart, and the fragments recombine into an enormous range of more complex organic molecules. Many of those molecules eventually clump together into solid aerosol particles called tholins, which drift downward and coat Titan's surface in a thick, hazy orange organic residue, essentially an entire moon slowly being dusted in the raw chemical building blocks that, on early Earth, are thought to have helped kickstart the chemistry of life. That haze is thick enough that it was the single biggest obstacle facing every spacecraft that ever tried to photograph Titan's surface directly. A persistent orange smog sitting over the entire moon that early flyby missions simply couldn't see through, and it took specialized infrared cameras and eventually a radar-equipped probe descending straight through the haze before scientists could finally confirm what was underneath it. Beneath the surface, gravity measurements and subtle patterns in Titan's rotation strongly suggest there's an actual liquid water ocean hidden inside the moon, tens to possibly hundreds of kilometers underground, likely kept from freezing solid by dissolved ammonia acting the way antifreeze does in a car radiator. None of Titan's hydrocarbon lakes or its deep, hidden water ocean is where scientists expect to find the most interesting chemistry, though. That distinction goes to something rarer and much more temporary. When an asteroid or comet strikes Titan's surface, the impact can generate enough heat to briefly melt a mixture of water ice and surface organics into a liquid pool, and depending on how thick an insulating layer of ice eventually forms over the top of it, recent modeling of one particular impact site, called Selk Crater, suggests these melt pools could stay liquid for anywhere from hundreds of years up to tens of thousands of years before finally refreezing solid. That's a long enough window, in principle, for genuinely complex prebiotic chemistry, reactions between water and organic molecules that can start building toward amino acids, the nucleobases that make up genetic material, and other biologically relevant molecules, all without needing life to already exist to make it happen. NASA is sending a mission specifically built to test that idea directly. Dragonfly is a car-sized, nuclear-powered rotorcraft, essentially a drone the size of a small vehicle, scheduled to launch no earlier than 2028 and arrive at Titan sometime in the mid-2030s. Rather than landing once and staying put the way most planetary landers do, Dragonfly is designed to fly from location to location across Titan's surface, making it what NASA calls a relocatable lander. Its primary destination is Selk Crater itself, an 80-kilometer-wide impact basin sitting almost exactly on Titan's equator, chosen specifically because it's one of the best candidate sites where ancient liquid water may have mixed directly with the organic material raining down from the atmosphere above. Zibby Turtle, the mission's principal investigator at the Johns Hopkins Applied Physics Laboratory, has been careful and precise about what Dragonfly is actually built to do, and just as importantly, what it isn't. Dragonfly isn't a mission to detect life, she's explained. It's a mission to investigate the chemistry that came before biology here on Earth. The spacecraft carries an instrument called DRAMS, the Dragonfly Mass Spectrometer, built specifically to analyze surface and subsurface samples for amino acids, nuclear bases, and other molecules that matter to biology, whether or not anything living ever made use of them. The fact that Dragonfly flies, rather than simply landing once and staying put, matters more than it might first seem. Every other mission covered in this video, from Curiosity crawling slowly across Gale Crater to Cassini's carefully plotted orbital flybys of Enceladus, has had to work within the limits of either a stationary lander or a spacecraft that can only sample whatever happens to drift past it in space. Dragonfly, once it arrives in the mid-2030s, will be able to hop from site to site across dozens of kilometers of Titan's surface over the course of its mission, sampling dune fields, crater floors, and whatever else lies along its route, building up a genuinely three-dimensional picture of how Titan's organic chemistry varies from place to place, rather than relying on a single fixed vantage point. That's a capability nothing has ever had at any of the other worlds in this video, and it's part of why Titan, despite being colder and more alien than almost anywhere else on this list, may end up being the single best-studied prebiotic chemistry laboratory humans have ever had access to. Titan's significance to this whole story isn't limited to what Dragonfly might eventually find when it lands. Recent sample return missions to two entirely different, much smaller bodies, the asteroids Ryugu and Bennu, have already confirmed that amino acids like glycine and alanine can and do form naturally on small, airless rocks drifting through space, with no water, no atmosphere, and no biology involved at all. That finding matters enormously for how scientists think about Titan, because it strengthens the case that the complex organic chemistry blanketing Titan's surface isn't some freak occurrence unique to one moon. It may be closer to a routine, expected outcome of basic chemistry, playing out on any world with the right raw ingredients and enough time, and Titan happens to have more of both than almost anywhere else scientists can currently study up close. Selk Crater and its equatorial dune fields aren't the only place researchers are watching closely either. A separate body of research has focused on Titan's polar regions, where geological evidence points to a higher concentration of cryovolcanic formations, areas where icy material may erupt from below the surface the way molten rock erupts from a volcano on Earth, just with water ice standing in for lava. Some researchers have proposed that in these polar cryovolcanic zones, prebiotic molecules produced through bursting bubbles at the surface of exposed liquid could get carried upward into Titan's atmosphere and then redistributed globally by Titan's version of large-scale atmospheric circulation, a process similar to Earth's Hadley cells. That would mean Titan's chemistry isn't just something happening locally at a handful of scattered impact sites. It could be a moon-wide system, continuously generating organic material in one region and physically transporting it to others. Dragonfly itself is headed to the equatorial dunes and Selk Crater rather than the poles, chosen specifically because that combination of organic rich sand dunes and water ice-bearing impact material lets the mission sample both of Titan's two major prebiotic chemistry pathways, atmospheric deposition and impact-generated liquid water, in roughly the same general area. It's worth being direct about where the actual boundary of the evidence sits, though, because Titan sometimes gets talked about with more excitement than the current science actually supports. No evidence of life, in any form, has ever been found on Titan. There's ongoing speculative discussion in scientific literature about whether some entirely different kind of biology, one that used liquid methane or ethane as its solvent instead of water, could theoretically function at Titan's temperatures. But researchers who've actually modeled that possibility generally agree it would face serious obstacles, including chemical reaction rates that slow down dramatically in that kind of cold, and limited solubility for the biomolecules such a system would need. Titan isn't a moon where scientists are hunting for organisms right now. It's a natural laboratory for studying the chemical steps that come before biology even becomes possible, running in real time across an entire moon, and Dragonfly is being sent specifically to read that chemistry directly off the ground rather than guess at it from orbit. Before we get to the closest anyone's ever come to actually announcing life on another planet, it's worth going back 20 years earlier than that announcement, to the mission that started this entire argument in the first place, and to one scientist who spent the rest of his life defending a result almost nobody else believed. On July 20th of 1976, exactly 7 years to the day after humans first landed on the moon, NASA's Viking 1 lander touched down on a plane called Chris Planitia and became the first American spacecraft to survive landing on the surface of Mars. It's worth sitting with the symbolism NASA itself clearly intended by choosing that exact anniversary, a mission built specifically to ask whether life existed somewhere besides Earth, deliberately timed to land on the very date that marked humanity's own first physical step onto another world. A second lander, Viking 2, touched down about 6 weeks later, on September 3rd, at a site called Europa Planitia, roughly 4,000 miles away from the first site. Both landers carried something no previous Mars mission had ever carried, a dedicated biology laboratory, built specifically to test Martian soil directly for signs of active life. That laboratory ran 3 separate experiments, each based on a different method for detecting biological activity, and each one produced a different result. 2 of the 3 experiments came back largely negative or ambiguous. The third came back positive, and it kept coming back positive, in a way that nobody on the mission team was fully prepared to explain. That third experiment was called the Labeled Release Experiment, or LR, and its principal investigator was an engineer named Gilbert Levin, working alongside his co-experimenter, Patricia Ann Straat. The idea behind the LR experiment was straightforward. Take a sample of Martian soil, add a nutrient solution where the carbon atoms had been made radioactive, and then watch to see whether the soil released any radioactive gas afterward. If living microorganisms were present in the soil and metabolizing that nutrient solution, they would, in principle, release carbon dioxide gas containing that same radioactive carbon as a metabolic byproduct, and the instrument would detect it. Run the same test on sterilized soil or on a soil sample with no life in it at all, and nothing should happen. When Viking 1's LR instrument ran the experiment for the first time, on July 30th of 1976, it got a strong, immediate, unmistakable positive signal, radioactive gas being released from the Martian soil almost as soon as the nutrients were added. Levin and Straat ran the same test again. It happened again. When Viking 2's identical instrument ran the same experiment at a completely different landing site, 4,000 miles away, it produced a similar positive result as well. 2 separate landers, thousands of miles apart, both delivered a response that looked, on its face, exactly like what you'd expect from active biological metabolism. If the LR experiment had been the only instrument on board, the story might have ended right there, as announced discovery of life on Mars in the summer of 1976. But it wasn't the only instrument. Viking also carried a separate instrument called a gas chromatograph mass spectrometer, designed to directly detect organic molecules, the carbon-based building blocks life is made of, in the Martian soil. That instrument found essentially nothing. No organic molecules were detected at either landing site, at levels sensitive enough that its absence struck most of the science team as difficult to reconcile with the idea of living organisms actively metabolizing in the same soil sample just inches away. That contradiction split the Viking science team, and it never fully healed. Most researchers on the mission eventually concluded that the LR results, however striking, had to be explained by some unusual, non-biological chemistry unique to Martian soil, most likely an unidentified oxidizing compound that could mimic a metabolic response without any life being involved at all. Levin disagreed, and he kept disagreeing, publicly, for the rest of his life. At first, immediately after the mission, he described his own results cautiously, saying only that they were consistent with biology rather than claiming outright proof. But by 1997, after years of additional laboratory testing back on Earth, and after newer Mars missions had confirmed the planet was wetter and more Earth-like in its ancient past than anyone realized in 1976, Levin and Straat published a formal conclusion stating that they believed the Viking LR experiment had, in fact, detected extant microbial life on the surface of Mars. Levin held that position for the rest of his career, through decades of being, in his own telling and in the accounts of colleagues, treated as something close to a fringe figure within planetary science. Joel Levine, a NASA researcher whose 41-year career began with the Viking mission, later described what happened to Levin in blunt terms, saying he was marginalized and was actually regarded as a crackpot by the community, even though he's no crackpot. In 2012, an international research team that included Levin published a new statistical analysis, applying cluster analysis techniques to the original labeled release data, and reported that the pattern of results supported the interpretation that Viking's LR experiment had detected extant microbial life on Mars, adding fresh technical weight to Levin's decades-old argument without settling the debate. Levin continued making his case in public, including in an opinion piece for Scientific American published on October 10th of 2019, and he remained convinced of his interpretation until he died in July of 2021, at the age of 97. Even the moment Viking 1 first reached the surface carried a kind of nervous, hopeful energy that's easy to forget 50 years later. Joel Levine, a NASA researcher whose career began with the Viking mission and continued for 41 years afterward, later described the scene inside Mission Control as the first image of the Martian surface slowly came into view. We were sitting there and watching the first picture develop of the surface of another planet from that surface of the other planet. He recalled Carl Sagan, sitting nearby, breaking the tension with a joke about the possibility of finding elephants or giraffes wandering across the frame. Kidding, but only barely, about just how open the question of Martian life still felt to the people running the mission that day. Nearly 50 years on, the Viking argument still hasn't gone away, and if anything, it's picked up fresh momentum recently. Researcher Stephen Benner, discussing the mission's legacy in a February 2026 retrospective, offered a blunt assessment of how history may eventually judge Levin's minority position. He's actually going to be proven right, or at least, at this moment, he is proven right by the preponderance of evidence. That's a striking thing for a working scientist to say about a 50-year-old, still unconfirmed claim. And it's a reminder that the Viking debate isn't a settled piece of history sitting quietly in a textbook. It's an active argument, still being revisited by name in scientific retrospectives published in 2026, exactly the same way the ALH 8401 and phosphine and K218b stories are being revisited and re-argued in real time throughout the rest of this video. What's kept the Viking argument alive for nearly 50 years now isn't stubbornness alone. It's that the broader scientific picture around Mars kept shifting in directions that made Levin's minority position look less far-fetched with each passing decade. Scientists have since discovered so-called extremophiles thriving in conditions on Earth once assumed to be completely lethal to life. Organisms living deep beneath Antarctic ice, inside lakes of near battery acid alkalinity, clustered around scalding deep-sea hydrothermal vents, and buried in some of the driest deserts on the planet. Every one of those discoveries chipped away at the old assumption that Mars was simply too harsh for anything to survive there, and later missions, from Curiosity's discovery of an ancient lake system in Gale Crater to the 21st century evidence of a genuine Martian ocean covered earlier in this video, confirmed that early Mars really was wet, warm, and chemically rich enough to support life, exactly the kind of environment the Viking-era assumption of a permanently sterile Mars had ruled out from the start. None of that proves Levin was right, but it means the scientific ground underneath his old argument has shifted substantially in his favor since 1976, even if the specific chemistry behind his original result is still formally unresolved. We've spent most of this video on worlds that never quite crossed the line into producing anything anyone can confidently call life. Viking's labeled release experiment is the first genuine exception on this list, a real, repeatable, peer-reviewed positive result for biological activity that a working NASA scientist defended until the day he died, and that a minority of researchers still take seriously today. 20 years after Levin's landers touched down, another team of NASA scientists would stand in front of the world and make an even more direct claim. based not on a chemical reaction in the soil, but on physical evidence embedded in an actual piece of the planet itself. The rock at the center of this story began its journey roughly 4 billion years ago, when it formed as solidified volcanic magma on the surface of Mars, making it, by a wide margin, one of the oldest pieces of any planet that humans have ever been able to hold in their hands. For most of its existence, it just sat there, part of the Martian crust, until something liquid, almost certainly water, seeped through its pores at some point in that deep past and left behind deposits of carbonate minerals inside cracks and pockets in the rock. Then, roughly 16 million years ago, an asteroid or comet slammed into Mars with enough force to blast a crater into the surface and throw debris clear off the planet entirely, out past Martian gravity and into an independent orbit around the Sun. One fragment of that debris eventually crossed paths with Earth and fell into Antarctica, where it sat buried in ice for thousands of years, until a research team recovered it in the Allen Hills region in the 1980s. It was catalogued, per standard meteorite naming practice, as Allen Hills 84001, or ALH 84001 for short, and for about a decade it drew relatively little public attention, just one more Martian meteorite in a small collection of samples scientists had managed to identify. It's worth sitting with just how old this single object actually is, before getting into what scientists found inside it. Most rocks anyone will ever hold, anywhere on Earth, have been recycled, weathered, or reformed many times over across geological history. ALH 84001 formed as volcanic magma solidified on Mars roughly 4 billion years ago, and then sat there, essentially undisturbed, for most of the following 3.984 billion years, meaning it had already been sitting on Mars for nearly its entire existence before that 16-million-year-old impact ever launched it into space. In the time since that fragment landed in Antarctica, human civilization has existed for only the tiniest fraction of even its most recent chapter, the 16 million years since it left Mars. That's the scale of object a team of scientists sat down to examine in the mid-1990s, and it's part of why the 1996 announcement carried the weight it did. This wasn't a simulation or a remote spectral reading taken from millions of miles away. It was a physical, 4 billion-year-old piece of another planet, sitting in a lab in Houston, ready to be cut open and studied directly. That changed in August of 1996. A team of NASA scientists at the Johnson Space Center in Houston, led by David McKay along with Everett Gibson and Kathy Thomas Keppeter, published a paper in the journal Science, laying out 4 separate lines of physical evidence inside ALH 84001 that they argued, taken together, pointed toward ancient biological activity on Mars. First, the meteorite contained polycyclic aromatic hydrocarbons, complex carbon-based molecules that can be produced by living organisms, embedded in fresh fracture surfaces in a way that suggested they were native to the rock rather than contamination picked up on Earth. Second, it contained carbonate globules, mineral deposits that on Earth are frequently associated with microbial activity in groundwater. Third, and probably the most scientifically debated point of all 4, the carbonate globules contained tiny crystals of magnetite, an iron oxide mineral, and in their size and shape, a striking number of those magnetite crystals closely resembled the specific kind of magnetite that certain terrestrial bacteria produce internally as part of their own biology. And fourth, high-resolution electron microscope imaging revealed elongated, segmented structures that, at least visually, resembled fossilized microorganisms, tiny enough that they'd only recently become visible at all with the imaging technology available at the time. NASA didn't quietly publish this in an academic journal and let it filter out slowly. The agency held a formal press conference to announce it, with McKay unveiling the meteorite itself alongside NASA's Associate Administrator, Wesley Huntress, standing next to him. For a brief moment in the summer of 1996, possible evidence of life on Mars wasn't a headline from a tabloid. It was a claim being made, carefully and specifically, by working NASA planetary scientists, based on physical evidence pulled directly out of an actual piece of the planet. The scientific response arrived fast, and it was substantial. Timothy Swindle, a planetary scientist at the University of Arizona, ran an informal poll of more than 100 fellow scientists in the aftermath of the announcement to gauge the field's actual reaction, as opposed to the version playing out in headlines. What he found wasn't outright dismissal. As Swindle summarized it, on average, scientists thought that it was a completely open question whether or not there's been life on Mars, and were skeptical, but didn't think it was ridiculous. That's a genuinely unusual place for the scientific community to land on an extraordinary claim, neither embracing it nor laughing it off, but treating it as a real hypothesis that deserved to be tested rigorously rather than dismissed on reflex. And it was tested, relentlessly, by researchers all over the world, and each of McKay's 4 lines of evidence took damage over the years that followed. On the organic hydrocarbons, McKay's own team eventually conceded, in later published follow-up work, that this particular piece of the case was comparatively weak on its own. A separate 1996 study led by Ralph Harvey and Harry McSween reported evidence that the carbonate globules had actually formed at temperatures above 650 degrees Celsius, more than 1,200 degrees Fahrenheit, a heat level that would make any biological origin extremely unlikely, since no known form of life could survive forming structures under those conditions. The magnetite crystals held up as the single most persistent and hardest to fully dismiss piece of evidence in the entire case, and they still are today. Chris McKay, a different, unrelated planetary scientist at NASA's Ames Research Center, explained years later exactly what would have made the magnetite argument close to airtight. On Earth, magnetotactic bacteria produce magnetite crystals that link together in distinctive chain formations, something like a string of pearls, which they use internally to orient themselves along magnetic field lines. If researchers had found that same string of pearls arrangement in the ALH-84S-PO01 magnetite, Chris McKay said, it would be compelling evidence of past magnetotatic bacteria. Nobody has ever confirmed that specific chain structure in the meteorite's magnetite grains. Meanwhile, the worm-like, fossil-resembling structures that drew so much public attention turned out to be genuinely difficult to evaluate on their own merits, since researchers noted that shape alone, without additional supporting chemistry, is notoriously unreliable, because plenty of non-biological processes can accidentally produce objects that superficially resemble simple bacteria under a microscope. Nearly 3 decades later, the case remains formally unresolved, not because nobody's looked closely enough, but because every individual piece of evidence has a plausible non-biological explanation, and no piece has ever been definitively, permanently ruled out either. Everett Gibson, one of the paper's original co-authors, was still standing by the core interpretation 18 years after the original announcement, telling an interviewer there were signatures of possible biogenic activity within selected Martian samples. Kathy Thomas Keppeter, another of the original co-authors, offered what might be the most honest single summary of the entire 30-year saga, when she pointed out that maybe the deepest problem raised by ALH-84001 isn't really about Mars at all. It's that we really do not have a good working definition of what constitutes life, a gap in basic scientific definitions that makes it genuinely difficult to ever fully close the book on a claim like this one, no matter how many more decades of study go into it. Timothy Swindle's informal 1996 poll result is worth returning to here, because it captured something that turned out to describe the entire rest of this video just as accurately as it described ALH-84001 alone. Scientists, on average, treated the claim as a completely open question, genuinely skeptical, but never dismissive. That specific posture, taking an extraordinary claim seriously enough to test it relentlessly for decades, without ever either accepting it prematurely or writing it off out of hand, turns out to be the exact same posture the field has since applied to Gilbert Levin's labeled release results, to the Venus phosphine detection, to Enceladus's chemistry, and to the dimethyl sulfide argument over K218b that's still playing out today. ALH-84001 didn't just raise one specific unresolved scientific question about a single meteorite. It set the template for how every subsequent claim of possible extraterrestrial life would be handled, argued over, and kept alive for as long as the evidence justified it. A template this entire video has followed one world at a time. ALH-84001 never delivered a confirmed discovery of life on Mars. What it delivered instead was something almost as important for how this entire field operates: a real-world case study, in exactly how carefully and exactly how publicly an extraordinary claim about life beyond Earth has to be tested before science is willing to call it settled in either direction. Before we leave Mars and head further out, it's worth pausing on something that never happened on any of these distant worlds at all, and instead happened right here on Earth, because it's the reason scientists take places like Enceladus and Europa, and even the inside of a Martian meteorite, seriously in the first place. For most of the 20th century, biologists worked from a fairly narrow assumption about where life could exist, built almost entirely around conditions found on the surface of Earth: moderate temperatures, neutral pH, access to sunlight, or at least oxygen, and a reasonable supply of liquid water. Then, starting in the 1970s, that assumption started collapsing, one extreme environment at a time. In 1977, scientists discovered the first deep-sea hydrothermal vents in the Pacific Ocean, towering underwater chimneys venting mineral-rich water at temperatures that can reach up to 400 degrees Celsius, in complete darkness, thousands of meters below the surface, far beyond any reach of sunlight. Rather than finding a lifeless void, researchers found thriving ecosystems built around those vents: tubeworms, clams, crabs, and shrimp, all ultimately supported at the base of the food chain by microbes called chemoautotrophs, organisms that build their entire metabolism around chemical energy pulled directly from the vent water rather than sunlight. Some of the microbes living closest to the vents themselves, a category called hyperthermophiles, have been documented growing at temperatures as high as 113 degrees Celsius, a genuine world record for biological life, in water hot enough to instantly kill almost anything found on Earth's surface. The extremes kept getting stranger from there. Researchers have documented a bacterium, sometimes called Bacillus infernus, thriving nearly 2,700 meters underground, at pressure roughly 300 times what's felt at the surface, and in temperatures exceeding 117 degrees Celsius, an organism living its entire existence buried in solid rock, without light, without oxygen, and under crushing pressure that would instantly kill a human. Researchers working in Antarctica's dry valleys, some of the coldest, driest places on the surface of the planet, have documented microbial communities surviving frozen into permafrost and subglacial lakes sealed beneath kilometers of ice for what may be millions of years. In Chile's Atacama Desert, widely considered the driest non-polar desert on Earth, with some regions that can go decades without measurable rainfall, researchers have specifically searched for and found microorganisms adapted to survive punishing levels of ultraviolet radiation, conditions researchers have explicitly used as a working analogue for the Martian surface. And organisms have been found thriving in conditions of extreme salinity, extreme acidity, and extreme radiation exposure that, individually, would each be considered lethal to the overwhelming majority of life on Earth. None of these discoveries prove that anything is alive on Mars, or Europa, or Enceladus. What they did was permanently break the old assumption that habitability required anything resembling comfortable, Earth surface-like conditions. Every single world covered in this video, an ancient Martian lakebed, a 3-billion-year-old Venusian ocean, the crushing dark interior of Europa, the hydrogen and phosphorus-rich plumes of Enceladus, even the frigid methane lakes of Titan, sit somewhere on a spectrum of extremes that Earth's own extremophiles have already demonstrated life can survive in some form. That's precisely why NASA's own astrobiology programs treat Earth's most extreme environments as direct research analogues for these distant worlds, and why the discovery of chemical energy sources like Enceladus's hydrogen or Europa's rock-water interface gets treated by scientists as such a serious, credible signal, rather than dismissed outright. The bar for what counts as a plausible habitat for life has moved dramatically over the last 50 years, almost entirely because of what researchers kept finding, against expectation, in Earth's own harshest corners. Mars, it turns out, wasn't finished generating headlines even after ALH 84001, and it would take almost 30 years and an entirely different rover exploring an entirely different crater before the next genuinely significant Martian biosignature claim made its way into a NASA press conference. In July of 2024, NASA's Perseverance rover, exploring an ancient dry riverbed inside Jezero crater, came across a reddish, arrowhead-shaped rock, roughly 3 feet by 2 feet, that the science team nicknamed Chayava Falls. The rock sat inside a formation called Bright Angel, along the edge of Neretva Vallis, an ancient river valley about a quarter-mile wide that was carved by rushing water billions of years ago as it fed into Jezero crater, itself the site of an ancient lake. Perseverance drilled into the rock, sealed the resulting core sample into a titanium tube nicknamed Sapphire Canyon, and moved on. And it would take the science team roughly a year of painstaking analysis before they were ready to say publicly what they'd actually found. What made Chayava Falls stand out were 2 distinct features embedded in its surface, which the team nicknamed poppy seeds and leopard spots, small, dark, ringed blotches scattered across the reddish rock in a pattern nobody on the mission had seen anywhere else on Mars. Those spots turned out to be associated with organic carbon compounds and minerals tied to redox reactions, the same basic chemical process, involving the transfer of electrons between different chemical compounds that many microbes on Earth rely on directly for energy. In September of 2025, NASA held a press conference specifically to announce the findings, with Joel Hurowitz, an associate professor of geosciences at Stony Brook University and lead author of the accompanying paper published in the journal Nature, walking through the case in detail. Sean Duffy, at the time acting NASA administrator, didn't undersell the moment, calling it the closest we have ever come to discovering life on Mars, and describing the identification of a potential biosignature as a groundbreaking discovery. Even with language that strong coming from NASA's own leadership, the science team was careful, in exactly the same way every other announcement in this video has required, to draw a hard line between a potential biosignature and actual proof of life. Katie Stack Morgan, Perseverance's project scientist at NASA's Jet Propulsion Laboratory, framed the announcement the way responsible astrobiology always eventually has to. Astrobiological claims, particularly those related to the potential discovery of past extraterrestrial life, require extraordinary evidence. NASA uses an internal framework called the Confidence of Life Detection Scale, or CoLD scale, made up of 7 separate benchmarks a finding has to work through before the agency will treat it as strong evidence of biology rather than merely an intriguing possibility, and the Chayava Falls leopard spots, however striking, still sit well short of the top of that scale. Non-biological explanations for the exact same spots remain fully on the table, the same way they did for ALH 84001 in 1996, and for Enceladus's chemistry today. Scientists specifically noted that the leopard spot pattern could, in principle, have formed through purely inorganic chemical reactions between iron, sulfur, and phosphorus minerals, reactions that happen to closely resemble what biology tends to leave behind, without any organism ever being involved. What makes Chayava Falls different from ALH 84001, in one important respect, is where the actual proof might eventually come from. The rock itself is 3.5 billion years old, roughly the same age as some of the earliest confirmed evidence for life here on Earth, and the Sapphire Canyon sample drilled from it is one of dozens Perseverance has been caching in sealed tubes across Jezero crater, specifically so that a future Mars sample return mission could eventually bring them back to Earth, where scientists could run laboratory analyses far more sensitive and definitive than anything a rover can carry to the Martian surface. Unlike ALH 84001, which fell to Earth by pure geological accident 16 million years ago, Chayava Falls was chosen, drilled, and sealed on purpose, specifically because scientists already suspected it might matter, and specifically so that the debate over what it actually shows could eventually be settled with better instruments than the ones currently sitting on Mars. The Mars story doesn't stop there either. Right now, in the present day, there's a second, entirely separate active mystery playing out in the Martian atmosphere itself, and it's one NASA's own scientists openly admit they haven't solved. Since landing inside Gale Crater in August of 2012, Curiosity has carried an instrument suite called SAM, short for Sample Analysis at Mars, which includes a highly sensitive tunable laser spectrometer capable of detecting even faint traces of methane gas in the surrounding air. On Earth, the overwhelming majority of atmospheric methane comes from living organisms, which is exactly why its presence on Mars matters so much. Over roughly 3 Martian years, close to 6 Earth years of continuous monitoring, Curiosity's instruments picked up a background level of methane that rises and falls with the seasons, generally ranging between about 1/4 and 2/3 of a part per billion by volume, peaking predictably during the warm summer months in Gale Crater's northern hemisphere and dropping again each winter. Chris Webster of NASA's Jet Propulsion Laboratory, lead author on the paper describing that seasonal pattern, called it a genuine turning point in the investigation. This is the first time we've seen something repeatable in the methane story, so it offers us a handle in understanding it. This is all possible because of Curiosity's longevity. The long duration has allowed us to see the patterns in this seasonal breathing. Layered on top of that predictable seasonal rhythm, Curiosity has also detected sudden, much larger spikes of methane that don't follow any pattern scientists have been able to identify. The largest single spike ever recorded, in June of 2019, measured roughly 20.5 parts per billion by volume, roughly 40 times higher than the normal background level, and it showed up, then vanished again within days, with no clear explanation for where it came from or why it stopped. Making the mystery even stranger, methane readings at Gale Crater appear to shift depending on the time of day, showing up more at night and dropping during daylight hours, a pattern that one 2021 study attributed to the gas becoming trapped near the surface overnight, before dispersing as temperatures rise each morning. And in a twist that's confused the picture even further, the European Space Agency's ExoMars Trace Gas Orbiter, a spacecraft launched specifically to measure methane across the entire Martian atmosphere from orbit, has detected no methane at all, anywhere on the planet, at any time, a direct contradiction with what Curiosity keeps finding at ground level inside a single crater. Paul Mahaffey, the SAM instrument's principal investigator at NASA's Goddard Space Flight Center, summed up the honest state of the science in a statement that could apply just as easily to nearly every discovery in this entire video. With our current measurements, we have no way of telling if the methane source is biology or geology, or even ancient or modern. Scientists have floated several non-biological explanations that remain fully on the table, including methane trapped in subsurface ice deposits that periodically vents to the surface, or ongoing chemical reactions between rock and water deep underground. And in 2019, researchers specifically ruled out wind erosion of surface rocks as a possible source, narrowing the field of candidate explanations without closing it. Curiosity's team even ran a rapid follow-up test after that record-breaking 2019 spike, and within days, the reading had dropped back down to less than 1 part per billion, close to ordinary background levels, confirming the spike had genuinely come and gone, rather than reflecting some kind of instrument error. As if the atmosphere hadn't given researchers enough to argue about, Curiosity's SAM instrument turned up a second related puzzle involving oxygen. Over that same 3 Martian year monitoring period, the rover confirmed the baseline composition of the air at Gale Crater's surface, about 95% carbon dioxide, 2.6% nitrogen, 1.9% argon, 0.16% oxygen, and 0.06% carbon monoxide. But the oxygen level, like the methane, doesn't stay put. It rises and falls across the Martian year in a pattern that so far doesn't match any known chemical process scientists can point to. Sushil Atreya, a University of Michigan climate and space sciences professor and co-author on the study describing the finding, didn't downplay how strange the result looked to the team the first time they saw it. The first time we saw that, it was just mind-boggling. Nobody on the Curiosity team is claiming biology explains the oxygen swings, any more than they're claiming it explains the methane. But between an unexplained, seasonally shifting oxygen cycle and a methane signal that spikes without warning, disappears within days, and contradicts what an orbiting spacecraft is measuring from above, modern Mars is still capable of surprising the scientists studying it, more than 60 years after the first spacecraft ever reached it. What makes the methane and oxygen mysteries different from almost everything else in this video is timing. The Martian Ocean, the Venusian greenhouse collapse, ALH 84001's biogenic minerals, even the chemistry inside Enceladus's plumes, are all questions about what happened at some point in the deep past, whether billions of years ago, or, in Enceladus's case, chemistry that's likely been running continuously for a very long time but was only recently observed. The methane spikes and oxygen swings in Gale Crater are happening on a timescale of days and months, in the present moment, on a planet with an active rover sitting right on top of the source. That immediacy is exactly why Curiosity's science team keeps running follow-up experiments the moment a new reading comes in, rather than waiting years to publish a slow, careful reanalysis the way researchers have had to with Venus's clouds or a 30-year-old meteorite. Whatever is producing these signals is still happening on Mars right now, which means, unlike almost every other mystery in this video, this is one where the next piece of evidence could show up on Curiosity's instruments before this video even finishes uploading. With that live, unresolved mystery sitting on the planet right next door, it's worth stepping back and asking a bigger question. Is our solar system, with its ancient Martian ocean, its possibly once habitable Venus, its ice-sealed moons, and its still unexplained Martian gases, actually a special case? Or is it more likely that worlds like these are common, scattered across the galaxy in numbers we're only just now starting to be able to count? That question is exactly what's driving one of the most closely watched research programs in modern astronomy, focused on a small, dim, unremarkable-looking star called TRAPPIST-1, sitting about 41 light-years from Earth. It's a genuinely strange thing to sit with, that the star at the center of one of the most important habitability investigations in modern astronomy is invisible to the naked eye and would draw no attention at all from an amateur stargazer scanning the same patch of sky. TRAPPIST-1 was flagged as scientifically important starting in 2016, when astronomers discovered it hosts 7 rocky, roughly Earth-sized planets, an unusually large and compact planetary system for a star that's small and faint. 3 of those 7 worlds, named TRAPPIST-1d, TRAPPIST-1e, and TRAPPIST-1f, orbit inside the star's habitable zone, the distance range where a rocky planet could plausibly hold liquid water on its surface if it has the right kind of atmosphere. Since 2022, the James Webb Space Telescope has been running a systematic campaign specifically to check whether any of these 7 planets actually have atmospheres at all, and the early results have been genuinely mixed. The 3 innermost planets, TRAPPIST-1b, C, and D, appear most likely to be bare rock, with thin atmospheres at best, worlds that were probably stripped by the star's radiation and flares over billions of years. TRAPPIST-1 planets a small, cool type of star called an M-dwarf, and M-dwarfs like this one are known to produce far more frequent stellar flares than our own Sun, bombarding any close-in planets with enough radiation to strip away a fragile atmosphere over time. The planet drawing the most attention is TRAPPIST-1e, sitting almost exactly in the center of the system's habitable zone. Between June and October of 2023, an international research team observed TRAPPIST-1e with just on 4 separate occasions, watching starlight pass through the edge of the planet's atmosphere, if it has one, as it crossed in front of its star. The data turned out to be seriously complicated by what astronomers call stellar contamination, essentially interference from hot and cool active regions on the star itself, similar to sunspots, that can mimic or mask the kind of signal an actual planetary atmosphere would produce. It took the research team over a year of careful analysis just to try to separate the star's own signal from whatever the planet itself might be contributing. As of the most recent published results, the outcome remains genuinely ambiguous. The data doesn't provide strong evidence either for or against an atmosphere on TRAPPIST-1e, though it does weakly disfavor certain thick, carbon dioxide-rich atmospheres similar to the ones found on Venus or Mars today, and it rules out a hydrogen-dominated atmosphere containing carbon dioxide and methane. What the data does still permit is a nitrogen-rich atmosphere, similar in basic composition to Earth's own, carrying trace amounts of carbon dioxide and methane, which is about the most encouraging outcome the current data can support, without overstating what's actually been confirmed. The difficulty scientists are running into with TRAPPIST-1e isn't unique to that one planet either. TRAPPIST-1 itself is a small, cool star classified as an M-dwarf, and stars in that category are known to produce far more frequent flares than our own Sun does relative to their size, a side effect that's forced researchers to develop entirely new statistical techniques just to separate a real planetary signal from the noise generated by the star's own restless surface. Every single one of TRAPPIST-1's 7 planets is also tidally locked to its star, meaning the same side always faces the sun, the same way our moon always shows Earth the same face, which produces extreme, permanent temperature differences between a planet's day side and night side, and further narrows exactly how habitable any surface conditions could realistically be, even on a planet sitting inside the habitable zone on paper. Researchers have even proposed that the outermost of the 7 worlds, TRAPPIST-1H, might be worth studying less as a candidate for surface water and more as what one 2022 study called an exotitan, an icy, cold outer world whose atmosphere, if it has one, might behave more like Saturn's largest moon than like Earth. That comparison alone says something about how far this entire investigation has traveled over the course of this video. From an ancient ocean on Mars to a hypothetical, methane-hazed moon-like world orbiting a star 41 light-years from here, with genuine scientific reasoning connecting every step in between. Nobody studying TRAPPIST-1e is claiming to have found a second Earth. What they're doing is running the exact same kind of careful, incremental, argument-by-argument process this whole video has traced across our own solar system, just aimed at a star 41 light-years away. Instead of a planet or moon, we can actually send a spacecraft to visit. If TRAPPIST-1e does turn out to have a genuine atmosphere, and if future observations can nail down its composition with more confidence than the current, contamination-limited data allows, it would mark the first time scientists ever confirmed an atmosphere on a rocky, potentially habitable planet outside our own solar system, a milestone astronomers have been working toward for decades. TRAPPIST-1e isn't the only exoplanet that's generated this kind of careful, contested excitement in recent years, and it isn't even the loudest. A different world entirely, one that's produced the single most public biosignature debate since the Venus phosphine controversy first broke in 2020, involves a planet called K2-18b, and unlike almost everything else covered so far in this video, the argument over what it actually shows is still actively unfolding as of the most recent published research, with new papers arriving on the subject every few months. Where TRAPPIST-1 sits close enough to Earth, at 41 light-years, that its planets can at least in principle be studied one by one, K2-18b sits inside a completely different category of world that doesn't have a true counterpart anywhere in our own solar system, which is part of why it's drawn so much scrutiny. K2-18b is what astronomers call a sub-Neptune, larger than Earth but smaller than Neptune, a size and type of planet with no true equivalent anywhere in our own solar system. It orbits inside the habitable zone of its star, and in 2023, a research team led by Niku Madhusudan, an astrophysicist at the University of Cambridge, used JUST to detect methane at high confidence and carbon dioxide at a more moderate confidence level in the planet's atmosphere. Combined, that chemistry was interpreted as consistent with what's called a Hythian world, short for hydrogen and ocean, a hypothetical class of planet covered by a genuine liquid water ocean sitting underneath a thick, hydrogen-rich outer atmosphere. Tucked into that same 2023 data was something else, a much weaker, low-confidence signal that appeared to match dimethyl sulfide, a gas known on Earth as a biosignature because it's produced almost exclusively by marine phytoplankton and ocean-dwelling bacteria. That first DMS hint was genuinely weak, detected at only about 1 sigma confidence, a level of statistical significance that most astronomers would ordinarily just call a non-detection rather than a real signal. Even so, it was intriguing enough that other researchers started building follow-up models specifically to test whether it was even physically plausible. A 2024 modeling study led by researcher Tsai and colleagues used a climate and photochemistry model to check what level of biological activity a hypothetical Hytzian ocean would need in order to produce a DMS signal strong enough for JHERTS to actually detect it, and found that the number was enormous, roughly 20 times the total biological productivity of Earth's own oceans today. That's not a number that rules the possibility out entirely, but it's a useful reality check on just how much biology, in this hypothetical scenario, the data would actually require, and it added one more layer of quantitative scrutiny to a claim that was still, at that point, resting on a single, weak, 1 sigma signal. Madhusudan's team kept observing the planet anyway, and in April of 2025, they announced they'd found something stronger. Using a second JUST instrument, sensitive to a different range of infrared wavelengths, they reported detecting dimethyl sulfide, or possibly a closely related molecule called dimethyl disulfide, at roughly 3 sigma confidence, and at concentrations described as needing to be thousands of times higher than DMS levels found in Earth's own atmosphere to explain the data. Madhusudan didn't hedge when he presented the results publicly. Based on the new detection and the planet's position inside its star's habitable zone, he concluded the most logical explanation was a planet covered in a warm water ocean that was, in his words, teeming with life. He also pushed back directly against the instinct to assume Earth's own biology sets the only reasonable bar for what counts as a biosignature elsewhere, arguing, looking for what's biological on Earth isn't a good guide to what might be biological elsewhere. The response from the rest of the exoplanet research community arrived almost as fast as it had after the original 2020 Venus phosphine announcement, and it followed an almost identical pattern. Independent teams went back into the same publicly available JUST data and started running their own reanalyses. One reanalysis, led by researcher Schmidt and colleagues in 2025, confirmed the methane detection at high confidence, but found no statistically significant evidence for either the carbon dioxide or the original DMS signal from the 2023 data. A separate team, publishing under the pointed title K2118b, does not meet the standards of evidence for life, ran their own independent data reduction and spectral analysis, and found that the majority of their retrieval methods, 87.5% of them by their own count, did not support the DMS or DMD's detection at all. That same team found that the supposedly biosignature molecule was, in their analysis, statistically interchangeable with an entirely different, non-biological molecule called C2H4, meaning the data alone couldn't reliably distinguish between the two. Their conclusion was blunt. What looked like a big spectral feature in the mid-infrared data was more likely explained by leftover instrument noise than by any real signal coming from the planet's atmosphere at all. Other researchers attacked the underlying Hycean ocean interpretation from a completely different angle, independent of the DMS argument entirely. Several separate modeling studies published through 2024 argued that the original 2023 chemistry, the specific ratio of carbon dioxide to methane, and the absence of ammonia in the atmosphere, doesn't actually require a liquid water ocean to explain it at all. One alternative model proposed the missing ammonia could just as easily be explained by a deep hydrogen atmosphere sitting above a magma ocean, with no liquid water involved anywhere in the picture. Another proposed that an ordinary, gas-rich mini-Neptune with extra water vapor deep in its atmosphere could reproduce the same chemical ratios Madhusudan's team had measured, again, without needing a Hycean ocean at all. By July of 2025, the debate had grown large and contentious enough that NASA stepped in to help coordinate a more structured resolution, similar in spirit to what happened with Venus's phosphine controversy 5 years earlier. A new study led by Renyu Hu at NASA's Jet Propulsion Laboratory, working alongside Madhusudan's own team and other independent groups, combined 4 brand new JUST observations of K218b with the existing data and had 3 separate research teams each run their own independent Bayesian analysis, rather than relying on a single team's methodology. Hu described the reasoning behind that approach plainly. We always strive to test the robustness of our findings, and one of the best ways to do that is through independent analyses by multiple teams. The resulting study confirmed K218b genuinely does have a water-rich, chemically complex atmosphere, but found no conclusive evidence for dimethyl sulfide after all, tempering, though not entirely closing, the excitement that had built up since 2023. As of the most recent research available, K218b sits in almost exactly the same place Venus sat for years after 2020, a real, published, peer-reviewed detection claim made by a serious research group using real data that a wide swath of the rest of the field has not been able to independently confirm using the same evidence. One research paper laid out why that gap matters so much for the field's long-term credibility, warning that a proliferation of false positives would not only stall progress by forcing stricter detection thresholds, but could also erode public trust in astrobiology and the scientific process as a whole. That's precisely the tightrope every single discovery in this video has had to walk. The pull between genuine, career-defining excitement over a signal that might be real, and the slower, more careful, more skeptical process required before the entire field is willing to say, out loud, that the search for life beyond Earth has finally succeeded. Before we tie all of these worlds together, it's worth pausing on the two ideas that quietly ran underneath every single story we just covered. Because scientists don't go looking for life at random, they go looking based on a specific, testable framework, and understanding that framework is what makes the difference between a wild guess and a serious scientific claim. The first idea is the habitable zone, sometimes called the Goldilocks zone, the range of distances around a star where a planet could plausibly hold liquid water on its surface, not too close that everything boils away, not too far that everything freezes solid. Earth and Mars both sit roughly inside our Sun's habitable zone, which is part of why Mars gets so much scientific attention. Venus sits right on the inner edge of it, close enough that a shift in atmospheric conditions was apparently enough to tip it into a runaway greenhouse. But the habitable zone concept, useful as it's been, only accounts for worlds that get their heat from starlight. It has nothing to say about a moon like Europa or Enceladus, sitting far out past Mars, in the deep cold of the outer solar system, well outside any conventional habitable zone. Those worlds stay liquid on the inside, not because of sunlight, but because of tidal heating, the friction generated internally as a large planet's gravity repeatedly squeezes and flexes a smaller moon on an elliptical orbit. That single realization, that heat doesn't have to come from a star, is part of what quietly reopened the entire search for life in our solar system over the last 3 decades, and pushed it out past Mars and into the ice-covered moons of the outer planets. The second idea is the biosignature, some detectable signal, chemical or otherwise, that points toward the presence of life without necessarily proving it outright. Oxygen and methane sitting together in an atmosphere in quantities that shouldn't be chemically stable without something constantly replenishing them, phosphine or dimethyl sulfide showing up somewhere they have no obvious non-biological source, magnetite crystals shaped exactly the way certain bacteria manufacture them internally, or a leopard-spotted pattern of redox chemistry in a Martian mudstone. Every single biosignature scientists currently know how to look for shares the same fundamental weakness, and it's a weakness that showed up over and over again in every story in this video. A biosignature is evidence, not proof, because there's almost always some non-biological chemical process that could, at least in theory, produce a similar signal. That gap between evidence and proof is exactly where the phosphine controversy has lived for 6 years running, exactly where the K2-18b argument is living right now, exactly where the ALH-8401 debate has lived for nearly 30, and exactly where the Enceladus hydrogen and phosphorus findings and the Chayava Falls leopard spots sit at this very moment, genuinely compelling, but not conclusive. It's worth understanding just how much the mood of this entire field has swung back and forth over the decades, because it explains why so many of these stories cluster so heavily in just the last 30 years. After the ambiguous, contested results of the Viking missions in 1976, and especially after Viking's organic molecule detector came back essentially empty, a large portion of the planetary science community settled into a period of real pessimism about the odds of finding life anywhere else in the solar system, treating Mars in particular as most likely sterile, and the question as largely closed for a generation. That mood only really broke in the 1990s and 2000s, driven by 2 separate developments arriving almost together: the growing catalogue of extremophiles proving Earth's own definition of habitable had been far too narrow all along, and the first hard evidence from missions like Galileo and Cassini that entire oceans of liquid water were sitting inside icy moons that nobody had taken seriously as habitats before. That combination is what reopened the entire search, pushed it out past Mars and Venus toward the outer solar system, and eventually out past the solar system altogether toward planets like TRAPPIST-1e and K2-118b. Every discovery covered in this video, in other words, isn't happening in a vacuum. It's happening because the working scientific opinion about where life could plausibly exist has been rewritten at least twice in the last 50 years, each time by evidence nobody had predicted in advance. This isn't a new problem for the field either, and the phosphine argument and the ALH 8401 argument both sit inside a much longer scientific tradition of exactly this kind of dispute. Gilbert Levin's labeled release experiment, all the way back in 1976, is the earliest and in some ways the purest example of it, a real, repeatable, statistically positive result that split its own science team and never got a clean resolution in either direction, even after the man who ran it spent the rest of his life defending it. The point isn't that any of these claims, Viking in 1976, ALH 84001 in 1996, phosphine in 2020, the modern methane spikes still showing up in Gale Crater, are secretly all correct. The point is that this is what real, functioning astrobiology actually looks like from the inside. It isn't a single dramatic announcement. It's a decades-long argument, conducted in public through competing peer-reviewed papers, where the goal isn't to win quickly, but to be right eventually, however long that takes. With that framework in mind, it's worth going back through everything we've covered one more time, because looked at side by side, these worlds and these controversies tell a more interesting story than any single one of them tells alone. Mars had liquid water, quite possibly an entire ocean's worth, sitting right inside the Sun's habitable zone, for at least 500 million years, sometime between 3 and 4 billion years ago. Climate modeling of that early Martian atmosphere, built around a period called the Noachian era, roughly 4.1 to 3.7 billion years ago, suggests an atmosphere dominated by carbon dioxide, somewhere around 94%, with several percent hydrogen and smaller trace amounts of methane, thick enough in combination to trap enough heat for liquid water to persist on the surface. That's about as close to Earth's own early conditions as any other planet in this solar system has ever gotten. And unlike every other world on this list, Mars eventually lost its atmosphere and its water almost entirely, leaving behind a dry, frozen, wind-scoured desert, where a research team can now spend months mapping ancient shorelines using orbital cameras because there's nothing left to disturb the 4 billion-year-old evidence. And yet modern Mars still isn't done surprising anyone. In 2024, Perseverance found leopard-spotted chemistry in a 3.5 billion-year-old rock that NASA's own acting administrator called the closest anyone has ever come to finding life there, a sample now sealed and waiting for a future mission to physically bring it home. And that same dry, frozen desert keeps producing an unexplained methane signal that spikes, vanishes, and shifts with the time of day, in direct contradiction with what an orbiting spacecraft measures from above, more than 60 years into the space age. Venus, sitting at the other edge of the habitable zone, may have kept liquid water on its surface for a genuinely staggering length of time, potentially 3 billion years, roughly 2/3 of the entire history of the solar system, according to the leading climate models. And then it didn't just dry up the way Mars did. It inverted completely into the single most hostile surface environment of any solid body we know of, hot enough to melt lead, crushed under pressure, equivalent to nearly a kilometer of ocean depth. If those models are correct, Venus stands as the starkest possible reminder that habitability isn't a permanent state a planet earns once and keeps forever. It's a fragile, temporary condition that has to be actively maintained and can be lost. And even now, in its clouds today, Venus is still generating exactly the kind of unresolved biosignature argument that keeps entire research careers occupied for years at a stretch. Europa and Enceladus both trade away the advantage of sitting in a star's habitable zone entirely, and make up for it with an advantage neither Mars nor Venus has. Their oceans are protected, insulated under kilometers of ice from the temperature swings, radiation, and atmospheric loss that eventually doomed the surface water on both inner planets. Enceladus, in particular, has assembled nearly a complete checklist of chemical ingredients associated with life, liquid water, organic molecules, usable chemical energy in the form of hydrogen, and phosphorus in striking abundance, all confirmed directly from real spacecraft measurements rather than inferred from modeling. Nothing on that list proves biology, but for the first time in the history of this search, nothing on that list is missing either. Titan takes the entire framework and steps outside it altogether, trading water for methane and ethane as its working liquid, and trading the search for life directly for the search for the chemistry that comes before life, the actual building blocks, forming continuously across an entire moon, whether or not anything is ever there to use them. Then there's the run of biological controversies that have played out entirely in the realm of interpretation rather than raw discovery, moments where the disagreement itself became the story. Gilbert Levin's labeled release experiment in 1976 gave Mars its first, and in some ways still its strongest, positive biological signal. One its own principal investigator defended until his death in 2021 without ever convincing a majority of his colleagues. ALH 84001, 20 years later, took that same basic argument and grounded it in a physical, 4-billion-year-old piece of the planet itself. 4 separate lines of evidence that each individually eroded under scrutiny while never quite being fully eliminated. Cheyava Falls, essentially a full generation after that, gave the same basic argument a name NASA's own leadership was willing to call groundbreaking in public, while its own project scientist, in the same announcement, insisted that extraordinary claims require extraordinary evidence. And the phosphine story on Venus, alongside its close cousin the dimethyl sulfide story unfolding right now on K2-18b, shows that this exact same pattern, bold announcement, aggressive rebuttal, competing reanalyses, years of uncertainty, isn't a relic of an earlier, less careful era of astrobiology. It's still exactly how the field operates today, on a planet 41 light-years away, just as much as it operated on our own planetary neighbor across 5 decades, from 1976 to 2025. None of these worlds, and none of these disputed signals, has delivered a confirmed discovery of life beyond Earth. Not one. But that's genuinely different from saying none of them came close, because by any honest reading of the actual published science, several of them came remarkably close. Close enough that professional planetary scientists, not enthusiasts, not journalists, are still building missions, still writing papers, and still publicly disagreeing with each other about exactly how close. Mars had the water, and still has an unexplained gas seeping out of its ground. Venus had the time, and still has an unresolved argument playing out in its own clouds. Europa has the volume. Enceladus has nearly every ingredient on the list. Titan has the chemistry running right now, in real time, across its entire surface. ALH 84001 is still sitting in a research facility, unresolved, 30 years after a room full of NASA scientists first suggested it might already hold the answer. And 41 light-years away, K2-118b is generating the exact same argument all over again, in real time, about whether a distant ocean world is quietly teeming with life, or whether a team of astronomers got ahead of what their instruments could actually prove. The search hasn't ended, and none of these worlds or claims should be filed away as closed cases. Europa Clipper is still on its way through the solar system, gathering data with every flyby. JUICE is doing the same. Dragonfly is still years from launch, let alone landing on Titan's equator. Missions are actively being designed right now specifically to finally settle the Venus question, one way or the other. JUST is continuing to stare at both TRAPPIST-1e and K2-118b, gathering the additional transits that might eventually turn a contested, low-confidence signal into something the whole field can agree on. And somewhere, right now, a research group is very likely re-examining old Cassini data from Enceladus, or old ALH 84001 electron microscope images, or a fresh batch of Curiosity's methane readings, looking for the one detail everyone else missed. Every one of these worlds went dark, or froze, or never quite crossed the final line, at some point in their history. But not one of them has been fully ruled out, and that's exactly why scientists keep going back. There's a pattern worth sitting with, now that all of it has been laid out side by side. Every single claim in this video, from Gilbert Levin's soil samples in 1976 to Niku Madhusudan's spectra from K2-18b just last year, followed almost the identical arc. Something looked, for a moment, like it might be the answer. A second team looked closer and found reasons to doubt it. A third team reanalyzed the same data and found a different result again. And the question stayed open, not because scientists gave up, but because they refuse to call something settled before the evidence actually earned it. That refusal is easy to mistake for failure, especially from the outside, especially when a headline promises life on another world and the follow-up story 6 months later quietly walks it back. But it isn't failure. It's the only method humans have ever found that reliably tells the difference between an exciting coincidence and an actual discovery. And every one of the 6 worlds and 4 controversies in this video is a live example of that method still running, right now, in observatories and labs scattered across the planet. So think back to where we started. Mars once held an ocean that may have rivaled the Arctic. Venus may have stayed as comfortable as Earth for 3 billion years before turning into the most hostile place in the solar system, and its clouds are still arguing with scientists about phosphine to this day. Europa is hiding twice Earth's ocean volume under ice that's never been drilled through. Enceladus has sprayed its entire chemical ingredient list directly into space for a spacecraft to taste. Titan is manufacturing the raw chemistry of life across its entire frozen surface without any water involved at all. A rock that spent 4 billion years on Mars and 16 million years drifting through space once convinced NASA scientists they were looking at fossils, and a different rock, drilled on purpose and sealed away just last year, is now sitting on the Martian surface waiting for a future mission to finally bring it home. A third Mars rock, breathing methane out of Gale crater right now, keeps contradicting what a spacecraft in orbit above it is measuring. And 41 light-years from here, 2 entirely different planets are each generating their own version of the exact same argument, in real time, about whether life has finally been found somewhere besides Earth. Every one of these worlds came close enough that the question is still open. None of them has closed it yet, and based on how many spacecraft are currently in transit, in development, or actively rereading old data as this video goes out, it's a safe bet that the next chapter in this exact story is already being written somewhere, right now, by someone who hasn't published their results yet. Maybe that's the most honest way to end a video like this one. Not with an answer, because there isn't one yet, but with an accurate accounting of exactly how close humanity has actually come, worked out one flyby, one drill sample, one reanalyzed dataset at a time, by people who kept showing up to the same hard question, decade after decade, without ever letting themselves round up to a conclusion the evidence hadn't earned. Every world in this video is still out there right now, exactly as it's been described here, still silent, still unconfirmed, and still, by any fair reading of the science, closer to an answer than almost anyone alive today was taught to expect. If this is the kind of story you want more of, worlds that almost made it, discoveries that never quite closed the case, subscribe and stick around, because there's no shortage of them left to cover.